Anti-lock braking, traction control and electronic stability control systems are now standard on most new cars. These systems add yet another level of electronic control to the increasingly complex modern vehicle. These modern control systems require very fast and reliable sensor data for peak performance when called upon. For many years, a magnetic induction sensor supplied the ABS control module with adequate data for wheel or vehicle speed. These are simple and reliable analogue sensors that generate waveforms at a frequency that is proportional to the wheel's rotational speed. A wheel turning at low speed produces a low frequency signal. As the wheel speed increases, so does the signal frequency. The sensor works by using a stator with a central permanent magnet and a soft iron core surrounded by an induction winding. The stator is positioned so that it has a very small clearance or air gap between the stator pole and a toothed rotor or tone wheel. As the tone wheel rotates, the air gap between the pole piece and the teeth change. As this occurs, the magnetic field or flux from the permanent magnet within the sensor will expand and contract in time with the approaching and receding tooth. The movement of the flux across the stator windings induces current flow in the stator circuit. The direction and size of the current flow depends entirely on the speed of the rotating tone wheel and whether a tooth is approaching or passing the stator. Let's slow this down a bit and look at each section of the waveform. With no movement of the tone wheel and the stator directly over a valley, there is no movement of the flux, so no voltage is produced. But as I rotate the tone wheel forward, the tooth approaches the stator. This influences the flux and causes it to move across the stator windings. A positive current is induced in the windings and flows in the circuit. This current and associated voltage will continue to build until the tooth is aligned with the stator pole. At this point, the magnetic flux is contracted as far as the tooth influence will allow, so movement of the flux ends. As there is no movement, current flow ceases and the voltage drops to zero. When the tooth moves past the stator, the flux expands once again and current flow is induced in the winding. This time, current flow is in the opposite direction and the polarity of the voltage is now said to be negative. Since polarity changes every time a tooth approaches and leaves the stator, the voltage and current flow in the circuit will alternate. It's the frequency of this voltage change that's used by the control unit to calculate wheel speed. Testing these sensors is relatively easy. We can use a multimeter set on ohms to check the resistance, or set on AC volts to check the output. My preference is an oscilloscope, as it gives me a complete picture of the sensor's ability to produce a clean analogue signal. Wheel speed sensor DTCs that are caused by opens, shorts or grounds can be easily checked with the multimeter, but any fault codes that relate to erratic operation, incorrect frequency or signal not plausible should always be checked with an oscilloscope. These codes are generally not caused by an electrical fault, but are logged because the control module doesn't recognise the signal pattern from the wheel speed sensor. The actual faults are generally mechanical in nature. Let's look at some of these now. The air gap between the stator pole and the tone wheel is the most important place to start your checks when diagnosing erratic signal fault codes. An air gap that is too large will not deflect the magnetic flux correctly. Correct signal will be produced. An air gap that is too small may cause debris to become lodged between the tone wheel and the stator pole, causing damage due to contact of the sensor and tone wheel. An incorrectly mounted sensor is not the only reason the air gap will change. A loose wheel bearing, hub or axle can cause the air gap to change when under load. Be careful when checking these air gaps with the wheel suspended. The air gap can vary quite a lot between loaded and unloaded suspension. While inspecting the air gap, be sure to check the tone wheel for damage security, and foreign debris in the teeth. Okay, if the mechanical side of the system checks out, connect the oscilloscope across the wheel speed sensor terminals. Spin the wheel and watch the trace. A correct signal should cycle between negative and positive volts, and the frequency of the shift should be proportional to the speed of the wheel. Something I do to help my diagnosis is to connect a second channel of the oscilloscope to the ABS control module. Because these sensors are in effect signal generators, the ignition should remain off and the ABS module can be disconnected for this test. Connect the second channel to the same signal wires from the wheel, but at the module end of the harness. Rotate the wheel and watch the scope. With the patterns overlaid, the trace should be identical. If there are any inconsistencies between the two, then there is a fault in the harness. Remember to check for terminal tension or any corrosion at the module connector, as either of these may set signal performance or erratic DTCs. If you have proved the sensor, harness, tone wheel and air gap to be okay, then the only possible fault can be the ABS control module. These old inductive systems have now been phased out. Their replacements have a faster response time. We call these magnetoresistive or active wheel speed sensors. The reason for the change is the widespread adoption of electronic stability control in new vehicles. ESP requires very fast signal interpretation to be effective. As active wheel speed sensors are digital in nature, an analog to digital converter within the control module is no longer required. Without the converter, the signals can be processed and acted on much faster. Active or magnetoresistive sensors look very similar to an inductive type. They have two terminals and are influenced by a moving magnetic field. But in operation, they're extremely different. The resistance value of an active wheel speed sensor is rated in megohms, whereas an inductive sensor's resistance value is much lower. This is because the stator in the active sensor is actually a magnetoresistive element. A reference voltage and ground are supplied to the sensor from the control module. These systems don't have a tone wheel. Instead, a multi-pole encoder ring is used. This encoder ring is designed as a multi-pole magnetic field. The segments are fixed alternatively north and south around the circumference of the ring. The encoder is sometimes formed as part of the wheel bearing seal, so it will rotate with wheel movement. The sensor assembly is mounted perpendicular to the encoder ring with a very small air gap. With the wheel stationary, one of the magnetic poles will always be in close proximity to the sensor. The magnetic flux from this pole will alter the resistance of the sensing element. The current flow through the sensor at this point will be about 7 milliamps. The control unit sees this as a fixed voltage. This voltage is assigned as signal low. When the wheel begins to turn, the next segment of the encoder ring influences the sensing element, changing its internal resistance. The current flow through the sensor will now be around the 14 milliamp area. The control unit sees this as a change in the circuit voltage drop and is programmed to recognise this as a signal high. As the wheel continues to turn, the change in current flow through the sensor is interpreted as an alternating voltage from low to high, or off and on. This is a digital signal. The speed of the change, or the frequency of the signal, is directly proportional to the wheel speed. This is a digital signal. The speed of the change, or the frequency of the signal, is directly proportional to the wheel speed. Unfortunately, we can't test these sensors the same as an inductive type. Because the sensor uses a magnetoresistive element, any resistance value of the sensor is too high to use accurately. But a multimeter can still be used. Start by disconnecting the suspect sensor and turning the ignition on. Check for the manufacturer's specified voltage across the two terminals in the harness connector. If you don't have the correct reading here, you probably have DTCs relating to circuit shorts, opens, or excess resistance. Diagnose and repair these first. If the meter displayed the expected value, disconnect the leads and switch the meter to amps DC. Connect the meter in series with the sensor. It doesn't matter which circuit you're connected to, the only difference will be the direction of current flow through the meter. You'll want to select a fairly low current scale on the meter. Now rotate the wheel at a steady speed. The meter should alternate between 7 and 14 milliamps. When there is no rotation of the wheel, the current draw should sit on either 7 or 14 milliamps. If the current flow is much lower than 7 milliamps and the voltage measured at the connector was correct, then excess circuit resistance in the sensor will be to blame. But what does it mean if the current value is fixed on the meter and the wheel's still turning? Let's look at these signals again, but this time using an oscilloscope. I'm going to back probe the high and low reference circuits of the control module with the scope. I'll need a fairly small voltage scale to see the shift between high and low. If I rotate the wheel, a square wave pattern will be seen. As soon as I stop the wheel rotation, the voltage will hold steady due to no influence of the encoder ring. As before, I am rotating the wheel, but the trace signal is fixed. There is no square wave pattern. The scope's giving us similar information to the multimeter, but in greater detail. From this, we can conclude that the electrical circuit is functioning correctly, as there is current flow in the circuit, but there is no magnetic field rotation to change the resistance value of the sensor. A mechanical problem is what we should be looking for. Check the sensor for any debris, rust, or corrosion that may affect or interrupt the magnetic field. Check the air gap and compare with the manufacturer's specifications. If these are okay, check for any wheel bearing play that may affect the air gap. Check for any physical damage to the sensor and check for any water intrusion into the sensor harness. It might be worth asking if the vehicle's had any repair work done. Has an incorrect wheel bearing been fitted? Has a correct wheel bearing been fitted incorrectly? Diagnosing an active or inductive wheel speed sensor fault is not complicated once you understand how it works. Thanks for watching.